Welcome to another class of process heat transfer. In this lecture, I will talk about the introduction of the double pipe heat exchangers. Then I will discuss about some formulas and some correlations related to the film coefficient for the tube side as well as for the annular side. And I will also explain about the importance of the equivalent diameter and the caloric temperature. And this caloric temperature would be particularly useful for the determination of the fluid properties in the tube side as well as in the annular side. I will also present some formulas that can be useful for the determination of the pressure drop in the heat exchanger. Second last topic of this lecture would be the design steps. These design steps are very important, and I would suggest everyone to memorize these 14 steps because these are very useful and very helpful for the design of the heat exchanger. So these design steps are very important, and it can be applicable for the double pipe as well as the shell and tube heat exchanger. And at the end, I will explain about the design problem for the double pipe heat exchanger. Let's have a look on the geometry of the double pipe heat exchanger. So this is the simplest geometry that is related to the double pipe heat exchanger, and it has the flow direction, which is counter current flow, and one of the fluid is moving in the left direction and the other fluid is moving in the right direction, right? So this pipe is known as the inner pipe, and this pipe is known as the outer pipe, and the area between the inner pipe and the outer pipe at this position where my cursor is at right now, this area is known as the annulus. So this is the cross-sectional area of the double pipe heat exchanger, right? So this is the inner tube, right, and this is the outer tube. So there is the empty area between the inner tube and the outer tube from which the primary fluid is moving. This is known as the annulus region or the annular area, right? So in order to increase the heat transfer rate, so there are some extended surfaces or fins present on the outer wall of the inner pipe. So this is somewhat known as the extended surfaces, right? So this is a double pipe heat exchanger, and this is a double pipe heat exchanger with extended surfaces or fins on the inner pipe. There may be the bundle of tubes. So in the first two configurations, there is only one tube inside the outer tube, and in this configuration there are number of tubes or a bundle of tubes inside the main outer tube, right? So these tubes may have a simple configuration, or these simple tubes may have the extended surfaces or known as the fins on the outer diameter of the inner tubes, right? So this is extended form of the double pipe heat exchanger. The previous one was the very simplest design of the double pipe heat exchanger. So this is the double pipe heat exchanger, and it has a name of hairpin double pipe heat exchanger. So the name hairpin comes from the simple name with the hairpin that can be used to pin up the hair. So from that, this configuration is similar to that of the hairpin, so that's why it is known as the hairpin double pipe heat exchanger. So this is the outer pipe, right, and there is the inner pipe or the smaller diameter pipe inside this outer pipe, right? So it has the configuration, right? This is the inlet or the tube nozzle connections from where the tube fluid is entered, and it will move in this direction and it will move out from here, right? And this is the inlet and the outlet of the shell side. This configuration is the schematics diagram, and let me just show you the actual hairpin double pipe heat exchanger. And this is actually the double pipe hairpin heat exchanger, and it is actually available in both finned and bare tube designs. Fins means the inner tube has the extended surfaces that is used to increase the heat transfer rate, and the shell size, which is ranging from 2 inches to 6 inches IPS standards. And the applications include ideal for all sphere operating conditions, a simple low cost, and a section is also available for the standard petroleum and petrochemical and the chemical services. So this is the simplest configuration of the double pipe heat exchanger. Hairpin double pipe heat exchanger. The hairpin double pipe heat exchanger can be used in series, right? So there are series configuration as well. This is one hairpin double pipe heat exchanger. So this is the inlet and the outlet of the inner tube, right? And this is the inlet and the outlet of the outer tube or the shell side, right? So the finned and unfinned double pipe heat exchanger. So this is the cross-sectional view of the bare tube inside the shell. So as you can see that there are no extended surfaces on the outer diameter of the inner tubes. So this is the bare tube double pipe heat exchanger, hairpin double pipe heat exchanger, as this is the diagram, which is the cross-sectional view of the fin tubes inside the shell. So there are the fins or the external surfaces on the outer diameter of the inner tubes, right? And this is a more clear picture that shows you the extended surfaces on the outer diameter of the inner tubes, which can be used to enhance the heat transfer rate. So the multi-tube double pipe heat exchangers are also available, that the finned and the bare tube designs are available, and that is extensively used in the industry. So the shell sizes for the multi-tube double pipe heat exchanger ranging from 3 inches to 16 inches IPS standards. And the applications of the multi-tube double pipe heat exchanger include for the heavy oil, heating of the heavy oils and the asphalts to the lighting chemicals. So these are the few examples which are given at the end of this diagram, which shows that the available designs are also used for the high pressure gas heat transfer and for the processing of lethal and hard to contain fluids and gases such as hydrogen. Look on some advantages and the disadvantages of the double pipe heat exchangers. So there are multiple advantages, which include that it is good for the sensible heating and cooling with up to area of 50 square heat transfer area, and it is good for 1 or 2 fluids which are normally at the higher pressure, and it can be used at the sphere fouling conditions. So the cleaning of the hairpin double pipe heat exchanger is relatively easy compared to the other designs of the heat exchangers. So can achieve pure parallel or the counter flow arrangements, as I have already explained in the previous lectures, that the U-tube or the hairpin heat exchanger can handle the thermal expansion, and the extra units can easily be added when we have to use it in series. So the one thing, it is clear that it is also known as the U-tube heat exchanger or the hairpin heat exchanger because of its design or because of its construction. So there are few disadvantages, that it has a bulky design and it is little bit expensive compared to the other heat exchangers. So let's have a look on few other parameters that would be useful for the design of the double pipe heat exchanger. Consider this is the inner pipe, right, and this is the outer pipe, and the inner area of the inner pipe is represented by DI, right, because the inner pipe has the smaller diameter and it is represented by smaller d, and I stands for the inner diameter of the smaller diameter pipe, and D naught stands for the outer diameter of smaller pipe, which is represented by D naught, right, from this point to this point. And capital D is used for the bigger size pipe or the outer pipe or the pipe which has the bigger diameter, and di stands for the inner diameter of the bigger pipe. So here we are going to see that the cross-sectional area for the annulus flow. What is the annulus flow? So this is the inner pipe and this is the outer pipe. So the area between the inner and the outer pipe is known as the annulus, and the flow which is moving in this area is known as annulus flow, right? So how can we determine this area? So we have to determine the annulus area, annulus cross-sectional area. What we can do is we can determine the cross-sectional area of this outer pipe using the inner diameter di, and then we can use we can subtract this area of the inner pipe using its outer diameter, right? Because from this point, let me just zoom it, from this point to this point, this is the available area for the flow in the annulus region. So this is the di and this is the small d naught, right? So taking the difference between these two diameters, or simply the area, what is the area? Pi r square. So when you open it and you simplify it, you will get the area of the cross section for the annulus flow, which is equal to AC is equal to pi over r into di square minus d naught square. Another most important thing is when we discuss the fluid flow in the annulus, and the plural form of the annulus is annuli, and the important terminology is the equivalent diameter, right? The equivalent diameter. So when a fluid flows in a conduit having other than a circular cross section such as an annulus, it is convenient to express the heat transfer coefficient and the friction factor by the same type of equations and curves used for the pipes and tubes. To permit this type of representation of annulus heat transfer, it has been found advantageous to employ an equivalent diameter, which is represented by dE. An equivalent diameter is the 4 times the hydraulic radius, right? And the hydraulic radius which of a pipe is equivalent to the annulus cross-section area divided by its wetted perimeter. So this is the equivalent diameter. It is the 4 times the hydraulic radius. So 4 over here, 4 over here. The hydraulic radius is the ratio of the flow area in the annulus divided by the wetted perimeter. So when we extend this formula into another form, so we have to put the formula for the flow area, which we have developed in the previous slide. This is the pi over 4, the d2 square minus d1 square. So when we put over here, so here we have to put 2 pi r. 2 pi r is, let me just bring my pointer over here. So this is the perimeter, right? This is the perimeter. So the wetted perimeter is actually the circumference of the inner tube, which is represented by 2 pi r, right? 2 pi r. So the circumference of the inner tube is 2 pi r, and this d1 stands for the inner pipe. So 2 pi r is the wetted perimeter, which is the circumference of the inner tube. So when we put r, and we know that the radius of the tube is equal to the half of the diameter. When we put d over 2 over here, so ultimately this 2 pi r becomes 2 pi d over 2, right? This 2 will cancel out with this 2, and this will become pi d1, which is the wetted perimeter or the circumference of the inner tube in the double pipe heat exchanger, right? And this one, pi 4, and this area, d2 square minus d1 square, pi over 4 d2 square minus d1 square is the flow area which we have calculated in the previous slide. And after simplifying that, we will have the wetted perimeter or the hydraulic diameter is d2 square minus d1 square over d1. And similarly, in the pressure drop calculations, the friction is not only the result from the resistance of the outer pipe, but it also affected by the outer surface of the inner pipe. So the total wetted perimeter will become equal to, previously we have just used the circumference for the inner pipe, but here we have used the inner and the outer pipe. This is the equivalent diameter. The formula is same, right? The formula is same. This is the 4 which comes from here, right? And this pi by 4 into d2 square minus d1 square is the flow area, right? And this pi into d1 plus d2 is the wetted perimeter, or simply known as the frictional wetted perimeter. And this equivalent diameter dE dash can be used for the calculations where we perform the pressure drop, calculations in the design of the heat exchanger. But normally we will have to use this equivalent diameter when we determine the heat transfer rate or the heat transfer coefficient, right? So when we determine the pressure drop calculations, or when we determine the pressure drop in the heat exchanger, so there we have to use this equivalent diameter, and it has ultimately, after simplifying that, will become equal to d2 minus d1. So this is the slide which actually summarizes all the formulas, major formulas that can be used for the design of the double pipe heat exchanger. Here the hydraulic diameter for the heat transfer calculations and the pressure drop calculations for the annulus flow would be same as it is that I have explained in the previous slide, this one. And the equivalent diameter is the 4 times the cross-sectional area over the wetted perimeter, and this is the formula for the cross-sectional area, and this is the equivalent diameter, right? And after simplifying that, you will get this one formula. In the previous slide I said that, this was the d2 square minus d1 square over d1, right? So no need to worry about. So the next is the formula of the Nusselt number H, that is the convective heat transfer coefficient. It is very important that ultimately you have to determine the convective heat transfer coefficient, and it will lead you further for the design of other parameters in the double pipe heat exchanger. This is the equivalent diameter and the thermal conductivity. So this is the formula that can be used for the determination of the flow velocity in the annular region, right, which is the mass flow rate divided by the density multiplied by the cross-sectional area. Here the famous formula for the Reynolds number, you have already gone through all the formulas in the previous lectures. So the next thing is the determination of the film coefficient or the convective heat transfer coefficient for the tube side. So this is a famous formula. So I'm sure you have gone through the similar formula in the 4th lecture. So this is the Nusselt number, right? And the right hand side there are the number of parameters which are actually the fluid properties, right? And this formula would be useful for the determination of the convective heat transfer coefficient when the Reynolds number is less than 2100. It means that for the laminar region, for the laminar flow, this formula would be useful for the determination of this parameter, which is known as the convective heat transfer coefficient, which is HI, right? And for the turbulent flow, you have to use this formula, right? So In the upcoming slides, I will explain about the importance of the average temperature or the caloric temperature, and from the caloric or the average temperature, you will determine all these properties of the fluid. For example, this is the specific heat, this is the viscosity and the thermal conductivity, and the equivalent diameter and the mass velocity and viscosity, and this is the viscosity correction parameter. This parameter is known as the viscosity correction parameter, and if the viscosities are not much high, so you can take this parameter, only this highlighted parameter would be equal to 1, right? And from this formula you will keep the convective heat transfer coefficient on this side while taking conductivity on the other hand side and the diameter as well on the other hand side. You will get the value of the convective heat transfer coefficient for the tube side. There is another way to determine the film coefficient or the convective heat transfer coefficient for the inner tube by using this Kolban factor, which is known as JH, right? JH. So for this you have to use this graph, right? I will show you this graph when I will solve the design problem for the double pipe heat exchanger. So this is the simplified graph. You will see proper graph when you solve the particular problem related to the design of the double pipe heat exchanger. So what you have to do is you have to determine the Reynolds number and then length to diameter ratio, right, of the double pipe heat exchanger. So if you are in the laminar region, so whatever the value you have to put the value over here of the Reynolds number. Then for particular length to diameter ratio, draw the vertical line over here and then draw the horizontal line over here. You will get a value of the Kolban factor, which is known as JH. For example, this value is 10, right? This value is 10. I'm just giving you the example. So what you have to do is you have to keep all these parameters after putting the values. You have to keep all these parameters on this hand side and multiply it with 10, and on the right hand side you will ultimately left with the HI, which is the film coefficient for the tube side. So in this way you can get the value of the convective heat transfer coefficient. If you get the value of the Reynolds number, and by using this graph you can get the value of JH factor, which is the Kolban factor, and from the Kolban factor and this correlation you can get the value of the film coefficient HI. So determination of the film coefficient for the annulus region, right? So for the annulus region, this is the annulus region from this point to this point. So the area in between these two lines represents the annulus region. So this HI that we have determined so far, right? And for the determination of the HI we have used the inner area. So this is the HI which is at this point, or the inner tube, right? So for this we have used the inner area. But when we use the heat transfer rate equation, that is Q is equal to UA delta T, this is the famous equation that we use. So in this equation, this is the A, which is actually the outer surface area of the inner pipe, right? For the outer surface area of the inner pipe. And for this famous equation, the area is, I'm repeating once again, the area is the outer surface area of the inner pipe, right? So we have to determine the film coefficient based on this outer surface area rather than the inner surface area, right? Because in this equation we mainly use the surface area, which is this surface area, and this is the surface area which actually involves the transfer of heat between the hot fluid or the cold fluid between the inner pipe and the annular region. So in order to determine the film coefficient for the annulus region, so this is the basic formula and the simplest formula, you can simply memorize it. So this is the HI, you can easily determine from the previous correlation or from the previous graph. You can just put the values of the areas, or simply you can put the value of the inner diameter and the outer diameter. You will get the corrected value of the film coefficient. This is also known as the corrected value of the film coefficient, or the film coefficient for the annulus region. So the double pipe heat exchanger is extremely useful because it can be assembled in any pipe fitting shop from standard parts and provides the inexpensive heat transfer surface. So the standard sizes of the inner and the outer pipes for the double pipe heat exchanger, usually the IPS standards. So if the outer pipe is the 2-inch diameter and the inner pipe would be 1 into 1/4 diameter. So these are the standard combinations for the design of the double pipe heat exchangers. So what is the concept of the caloric temperature or the average temperature, right? Let me just explain it. What is the caloric temperature and why we use it. For example, if we have the double pipe heat exchanger, this is the outer pipe and this is the inner pipe, right? So what is going to happen, that the cold fluid is moving in the annular region and the hot fluid is moving in the inner pipe, right? Or the inner pipe. This is the inner pipe, right? And what you are going to see, that if we consider we have the hot fluid, or sorry, the cold fluid, which is entering in the annulus region or in the outer pipe, right? So it is at 99.1 degrees centigrade. So the inlet temperature is of the cold fluid is 99.1 degree Fahrenheit, right? And the outlet temperature of the cold fluid is, which is at this point, right, would be 129.2 degree Fahrenheit. So the temperature of the cold fluid will ultimately be increased by the transfer of heat from the hot fluid, which is at the inner tube or at the inner pipe, right? So what you will see, that at one point or at the entrance the temperature is 99.1 degree Fahrenheit for the cold fluid, and at the outlet of the double pipe heat exchanger the cold fluid will have 129.2 degree Fahrenheit. So there is the temperature change, almost 30 degree Fahrenheit temperature is changing from inlet to outlet. So when you are going to determine the fluid properties for the cold fluid, so the question is what temperature that you will use, right? Because either you have to use the inlet temperature or the outlet temperature. So why the temperature is so important? Because from the temperature we have to determine the fluid properties, right? So if we use, let me just take an example, if we use the inlet temperature, right, inlet temperature of the cold fluid, that is 99.1 degree Fahrenheit, and we use to determine this temperature for the specific heat, viscosity and thermal conductivity, and ultimately after putting all the values in the formulas we determine the film coefficient that would be equal to 156, right? This is the value of the film coefficient for the fluid, which is determined by taking the temperature at 99.1 degree Fahrenheit, right? So the question is why we are taking this temperature 99 point, why can't we take 129.2, right? So in this topic I'm just going to explain you that why we have to take the average temperature or caloric temperature. So if we determine the fluid properties at 99.1 degree Fahrenheit, the convective the film coefficient is 156, and if we determine this the outlet temperature, if we consider the outlet temperature and we determine the film coefficient, which will be equivalent to 190. So it means that at different temperatures, we will have different film coefficients, right? So at one point, at point 1 we have or at the inlet point we have the film coefficient 156 because of the temperature we have taken is 99.1 degree Fahrenheit. But at the outlet temperature, which is 129.2 degree Fahrenheit, the film coefficient is 190. Now the question is, which temperature is the correct temperature and which film coefficient is the right value, or which we can use it further for the design of the heat exchanger. So neither of the values, like 156 and 190, both the values are incorrect. So let's have a look at a third scenario. If we take the arithmetic mean of the inlet and the outlet temperature, so the inlet temperature is 99.1 and the outlet temperature is 129. If we take the average, so this is the average, and after taking the average we determine the film coefficient that will be equivalent to 174, right? So which is only 3.6% in error of the experimental value. So the experimental value of, or the correct value is of the convective heat transfer coefficient is 181, right? So there are total 4 scenarios. Let me just explain it to you once again. So we determine the film coefficient at the inlet temperature, which was 156. We determine the film coefficient at 129 degree Fahrenheit, which was 90 degree centigrade. So we don't know which we have to use because we don't have any idea that either we have to use the inlet or the outlet temperature. So we go for the arithmetic mean. So the film coefficient also changes, that will become equal to 174. So we have 3 scenarios, right? So when we determine this film coefficient value from the experiment, ultimately it will become equal to 181. So when we take the error between the experimental value and the film coefficient value, which was determined at the arithmetic mean temperature, so the error was only 3.6%, right? When we use the average temperature and we compare it with the experimental value, the average or the error was only 3.6%. So when we compare the inlet temperature value or the outlet temperature value with the arithmetic mean value, the percentage error would be minus 10.6% or plus 8.9%. So you have observed that which value would be useful. So it means that the nearest value for the heat transfer coefficient or the film coefficient would be the arithmetic mean value. So in order to determine the fluid properties at the average temperature or the caloric temperature, there are these two different formulas for the hot fluid as well as for the cold fluid, right? You have to use these formulas. So the T1 and the T2 are the inlet and the outlet temperature of the hot fluids, and the small T1 and the small T2 are the inlet and the outlet temperature for the cold fluid. So there is another parameter which is known as FC, which is known as the caloric fraction, which will be given in the figure number 17. In the upcoming slide, I will show you a small example related to the determination of the caloric temperature. For example, this is the graph that would be used to determine this caloric fraction, Kf value, and ultimately it would be used to get the value of actual caloric temperature. So here is this graph, the FC on the y-axis, and there is the Kc. I will show you how to use this graph, right? So this is the small example that how to calculate the caloric temperature, right? Let me just read the question statement that a 20-degree API, this is the specific gravity. Crude oil is cooled from 300 to 200 Fahrenheit. So it means that this is the hot fluid which is ultimately come outside the heat exchanger in cold form. So from 300 to 200 its temperature is decreasing. So by heating the cold fluid, so this fluid is heating the cold fluid which has the API gravity, that is 60-degree API gravity gasoline, and the cold fluid temperature is, inlet temperature is 80 and the outlet temperature is 120 Fahrenheit in the counter current flow apparatus. So at what fluid temperature you should evaluate the overall heat transfer coefficient, right? So we have to determine first of all the caloric temperature, right? So this is a table. In order to understand this table, so these are two columns. Remember, these are two columns. This is the first column, right? And this is the second column. So for the higher temperature, right? So for the shell side, so it is saying that the fluid temperature is, decreases from 300 to 200 Fahrenheit, right? From higher to lower temperature. So this is starting point, right, at the middle. So the shell side fluid which has the API gravity 20-degree API gravity crude oil, so its higher temperature is 300 and lower temperature is 200. So this is the higher temperature and this is the lower temperature. So temperature is decreasing from 300 to 200 Fahrenheit. So 300 to 200 Fahrenheit. Similarly, from for the gasoline which has the API gravity 60 degree and its temperature is increasing from 80 to 120. So what is the highest temperature for this fluid? 120 Fahrenheit is the highest temperature and 80 is the lowest temperature. So we put the gasoline column, the highest temperature is 120 and the lowest temperature is 80, right? So by taking the difference between the inlet and the outlet of the gasoline, the difference would become equal to 40, right? And this is the inlet of the gasoline, this is the outlet of the gasoline, right? And this is actually the cold fluid. The difference between the inlet and the outlet is 40, and this horizontal row is representing for the difference. So this is the hot fluid and the inlet of the hot fluid is 300 and the outlet is 200. The difference between these two will represent the 100, right? So the mean temperature is, what is the mean temperature? The average temperature. So if we take the average of 80 and 120 divided by 2, the average would be 100. And similarly, if we take the average of 200 and 300 and divided by 2, it will become 250, right? So all the values which are underlined are clear, right? So what is this 180 and 120? So this is the temperature difference between these two, right? So this temperature, the highest temperature difference, right? The highest temperature of the hot fluid, the highest temperature of the cold fluid, the difference between these two is 300 minus 120, that will be equal to 180, right? And the difference between the lowest temperature of the hot fluid and the cold fluid, 200 minus 80, that will become equal to 120. So this will be equal to delta T1 and delta T2. So keep in mind that in this table everything is clear. The delta T1 is clear, delta T2 is clear, the highest temperature is also clear, lowest temperature is clear, difference is clear, mean temperature is clear. So the last thing is the caloric temperature. So caloric temperature, that we have to determine it by using the formulas that is given in the previous slide. So let's just go to the next slide. So there are two fluids which is given in the question statement. The one is the crude oil, the second is the gasoline oil. So the crude oil inlet temperature is 300 and the outlet temperature is 200. So if we take the difference of the inlet and the outlet, that will be equal to 100. And this is for the crude oil. For the gasoline, the difference between the inlet and the outlet, right? This is the inlet and this is the outlet. So if we take the difference between the inlet and the outlet, and this will become 40. And it is also mentioned in the previous slide. For the hot fluid, the difference is 100, and for the cold fluid, the difference is 40. It is same. So we have to determine the value of Kc, which is the friction coefficient, which is actually the caloric friction. This Kc value from the figure number 17, right? So this is the first crude oil. For the crude oil, we will determine the value of Kc from figure 17. So let's have a look on the crude oil, which has the API gravity of 20 and the temperature difference is 100. So these are the two things that you need to keep in mind that when you go to the graph. So the one is the API gravity, that is 20, and the second thing is the temperature difference. So let's just go to the graph. So this is the graph. So first of all, to determine the value of Fc, you have to determine the value of Kc, and to determine the value of Kc, you need to get two things that I have said in the previous slide a few seconds ago. First you need to have the API gravity, which was 20 for the crude oil, and the temperature difference is 100. So this is, let me just bring it over here, my pen. So this is the API gravity, which is 20, right? And which line represents the 100° Fahrenheit temperature difference? So this is the second line. So this is the starting point, which is 20° API gravity. You go horizontally until you touch the 100° Fahrenheit line. So this is the intersection point, and then you will go downside to this point to get the value of Kc, right? Kc. So here the Kc value would become equal to 0.6 is here, 0.8 is here, this would be equal to 0.7, right? So the value of the Kc would be equal to 0.7, and here it is equal to 0.68, which is nearly equal to 0.7. And similarly for the gasoline oil, the API gravity is 60° and the temperature difference is 40. You go to this graph and you get the value of Kc for the gasoline, which is equal to 0.1. And then the second thing is, you have in the previous slide determined the difference between the hot fluid temperature and the cold fluid temperature, right? Delta T1 and delta T2, and after dividing it, you will get over here that is 0.667, right? So 0.667 is given here over here. So from the value of this temperature ratio, right, 0.667, and the value of this Kc, right, so what you will get is, you will have to get the value of Fc. How? So on the x-axis, this is the ratio of the temperatures, the delta higher temperature difference and the lower temperature difference. This is here up to some point 0.668. You will go upward until the point of Kc. The value of Kc was 0.7. It was in between this 1 and 0.5, and ultimately you will draw the horizontal line either on right hand side or left hand side. You will get the value of the Fc, that will be greater than slightly greater than 0.4, and if you zoom this graph, and ultimately you will come up with the value of 0.425. This is the caloric fraction value. Similarly, after getting the value of the caloric fraction Fc value, you will put into the formulas and you will get the value of the caloric temperature for the crude oil and the caloric temperature for the gasoline oil. So this is the temperature that is for the crude oil, 242.5° Fahrenheit and 97° Fahrenheit, and this is the actual caloric temperature. And these are the temperatures that you have to use for getting the values of the fluid properties like viscosity, like density, and etc. And finally, this is the fanning friction equation that will be used for the determination of the pressure drop, and this is the formula that is used for the determination of the velocity, and this is the mass velocity divided by 3600 is the conversion factor multiplied by its density. You will get the velocity, and for the annulus side, and the units of this velocity would be the foots per second, and ultimately this would be the formula that would be used for the pressure drop due to the velocity. So this is all about the introduction and the parameters and the correlations that would be used for the design of the double pipe heat exchanger. Now let's have a look on the design of the double pipe heat exchanger, where I put HE, that stands for the heat exchanger. So in the outline below that I will explain, the hot and the cold fluid temperatures are represented by the upper and the lowercase letters respectively. All the fluid properties are indicated by the lowercase letters to eliminate the requirement for the new nomenclature, and you have to use the similar nomenclature. For the hot fluid, we will have a T1 and T2 for the inlet and the outlet, and the cold fluid for the small T1 and small T2. This is the mass flow rate and specific heat, specific gravity, density, and so on. This is delta P. The diameter of the pipes must be given, or you have to assume it. Let's have a look on the design steps. I will explain the design problem in the second part of this lecture. Let's have a look on the generic look on the few design steps. So I will quickly read the design steps so that you will get the idea. So I will also bring the design steps one by one when I will explain the design problem for the double pipe heat exchanger. So the first step is you will be given with the inlet and the outlet temperature for the hot fluid and the cold fluid. So check the heat balance, right? And using specific heat and the T mean temperature, or it could be the caloric temperature, it could be the average temperature. So radiation losses from the heat exchangers are usually insignificant or compared to the heat load transferred in the heat exchanger. So the second step is determine the LMTD, log mean temperature difference, using these four temperatures, assuming the countercurrent flow, because in the previous lecture we have seen that for the countercurrent flow the LMTD would have the higher value. This is the third step and the most important step that you need to understand, that TC, capital TC and small tc, which represents the caloric temperature for the hot fluid and the caloric temperature for the cold fluid. I'm just going to read this step so that you will get the idea that this is the most important step in the design of the double pipe heat exchanger. If the liquid is neither a petroleum friction nor a hydrocarbon, the caloric temperature cannot be determined through the use of figure 17 or the equations for the caloric temperature which is given in the previous slide. Instead, the calculation of the clean overall heat transfer coefficient must be performed for the hot and the cold terminals, giving the U, H and the UC, from which may we obtain the value of Kc, and the value of Fc is then be obtained, and from the table 17 then we can perform the calculations further. The next important thing is, this is the actual point that I am going to explain in the design problem. If neither of the liquid is very viscous, it means that none of the liquid, either the cold fluid or the hot fluid, are viscous at the cold terminal, say not more than 1 centipoise. So if the viscosity is up to 1 centipoise or less than 1 centipoise, the liquids are considered as non-viscous. This is first point. Second point is, if the temperature ranges do not exceed 50 to 100 Fahrenheit, right? So previously we have seen that the temperature ranges when we determine the caloric temperature. So we have to see that either the caloric temperature for the hot fluid, the temperature range is in between 50 to 100, right, for the hot fluid and the cold fluid. This is the second point. And the third point is, and if the temperature difference is less than 50 degree Fahrenheit, so we have to use the arithmetic mean temperatures. What does it mean? Arithmetic means the average of the capital T1 and the capital T2. Instead of the capital T1 and the capital T2, and the average of small t1 and the small t2 may be used in place of the caloric temperatures for the evaluating of physical properties, because the liquid physical properties are very important, such as the density, such as the viscosity, such as the conductivity, and the other properties as well. These are very important properties. So if the temperature range do not exceed 50 to 100 degree Fahrenheit, this is first point, and if the viscosity is up to 1 centipoint, second point, if the temperature difference is less than 50, so this is the third point. If any of the point is fulfilling, so what you have to do is you do not have to go for the value of the caloric temperatures, just you have to go for the arithmetic mean temperatures, right? And the last point is, if the fluids are non-viscous or the less viscous, this is the viscosity correction parameter, and you can assume this parameter is equal to 1 while performing the calculation. So I have already explained this point when I was explaining the film coefficient for the tube side. So the fourth point is to determine the flow area in the pipe as well as in the annulus region for the double pipe heat exchanger. Fifth is to determine the mass velocity by dividing the mass flow rate divided by the flow area, right? And then obtain the viscosity value at the caloric temperature depending upon which flow through the inner pipe, right? And convert this value into centipoise. So from the figure, I will explain it in the design problem. From the figure, you will get the value of the viscosity in centipoise. You will have to convert it into this unit after multiplying it to 2.42, right? And the next, from the diameter, which is given in the fit, and from the mass velocity and from the viscosity, and you have to determine the Reynolds number. This is the sixth step. So in the sixth step, you have to use viscosity, you have to use the mass velocity, and you have to use the equivalent diameter, right? And the seventh step is you have to determine the JH Coulomb factor either from the graph, right? So the figure number 24 is given. I will also explain it how to use this graph to determine the JH factor. And the eighth point is from the specific heat and from the viscosity and from the thermal conductivity, you have to compute this parameter, right? So this is one of the parameter which is given in this equation, right? Because you have, once you will get the physical or the numerical value, this one, you will put it over here, and ultimately you will have to use this equation to determine the film coefficient, right? And the ninth step is also the same, to obtain the HI by multiplying the JH with the remaining parameters. So this is the JH parameter. Keep the HI on one hand side, remaining all the other parameters on multiplying with the JH, you will get the value of HI. Once you will have the value of HI, you will have to convert it for the annulus region. So this is the correction which I have already explained in the previous slide, that once you get the value of HI, you will have to convert it for the value of HI naught, right? And for the annulus region, you have, this is for the inner pipe, right? And for the annulus region, you have to follow the same steps. All the steps are same, but for the annulus region, you have to use the flow area, right, is different, and the equivalent diameter is different. But remaining all the other steps are same as for the inner pipe. The next is you have to determine the clean overall coefficient by using this formula. This is the film coefficient for the annulus region. This is the film coefficient which you have calculated from the shell side, and after calculating it, you have to determine the design overall heat transfer coefficient by incorporating the dirt factor, right? And then ultimately you have to compute the surface area, right? I will also explain each and every step again in the design of the double pipe heat exchanger problem. And finally, ultimately, you will have to determine the pressure drop, right? The pressure drop formula for the inner pipe is, you will have to get the Reynolds number, and after getting the Reynolds number value, you will have to, this equation, this is the fanning friction equation, and it is given over here, and the units ultimately you will get in fits, right? and in order to convert it into PSI, so multiply this parameter with the density divided by 140, you will get the pressure units in pressure drop units in the inner pipe would be equal to PSI. And similarly, for the annulus region, we have said that for the determination of the pressure drop, you have to use the different equivalent diameter, and we have determined this formula, and the remaining all the other parameters are almost same. This is the fanning friction equation, this is the Reynolds number, and after putting the value you will get the value of the fanning friction equation. And for the entrance and the exit losses and the velocity per head per hairpin, you will have to use this formula, and the frictional losses as well as the exit losses or the entrance losses, you will have to determine these two pressure drops. And after that, for the annulus side, you will have to add both of the pressure losses, and to convert it into the PSI, you will have to multiply it with this correction parameter or the conversion parameter, and ultimately you will have the pressure drop in the annulus region in the PSI. This is all about the design steps for the double pipe heat exchanger. This is the first two steps, and this is the third step, is the most important step. These are from 4 to 10 steps for the inner pipe, and this is these are the design steps for from 4 to 9 in the annulus region. And this is the overall coefficient for the clean overall coefficient, design coefficient, and the surface area. And this is the slide which represents the pressure drop calculations for the inner pipe as well as for the annulus region. From this, the first part of this lecture is over. In the next part, I will explain about the design problem for the double pipe heat exchanger.